This is Simulating Europium Zinc Arsenide to Investigate the Tautological Properties that Arise Under Pressure by Amaya Caudel under the guidance of Dr. Fei Xu, Dr. Jia Shi, and Naomi Falcons at the University of Alabama at Birmingham. The abstract section is just a summary of the story so far in this process. So, Dr. B's lab here at UAB were looking at europium zinc arsenide under intense pressure when they found interesting properties that may be topological, like features in the absorption spectra or a large increase in the magnetic ordering temperature with the increase of pressure. They're thinking that the band gap in the material, which is naturally small in the first place, shown by Wang et al., is closing under this pressure, making this a Dirac-like state, and that's what's causing these interesting properties. To look behind the curtain at what's actually happening inside the material during this process, we are computationally recreating their experiments to calculate the band structure. When Wang et al. Presented their findings, they also detailed the methods they used to get those. So our first step was to recreate their band structure exactly to know our results are sound in ambient conditions before we move on to pressure. To do this, we used the Vienna-Abenido simulation package, or VASP, to run the first principles quantum mechanical calculations, and visualization for electronic and structural analysis, or VESTA, to view and build the materials. The supercomputer we use to run VASP is the high-performance computing cluster here at UAB, CHIHA. We have gotten results that are consistent with the literature so far in our process, though we haven't yet been able to add the spin-orbit coupling due to the time constraints of the REU. After this program is over, the next thing we'll be working on is the pressure varied calculations to compare with the results of that of Dr. B's lab. So as for where we start here, the reference paper we're going off of presents europium zinc arsenide as an analog to europium cadmium arsenide, which we already know is a Dirac semimetal, which in a Dirac semimetal the bands close at a point called a Dirac point. Comparing that to Dr. B's lab data, their findings suggest that under enough pressure the bands close in the zinc material as well, making it function similarly to the cadmium material. This leads us to our hypothesis. Does exposing europium zinc arsenide to enough pressure close the band gap? To test this, we will be simulating the material under a range of pressures and comparing the results of each test. But to start, we first had to replicate the band structure from the reference paper using the same setup that they used. The steps being, relax the structure, then add the Hubbard U energy offset, then add spin-orbit coupling. Then, once that's down, we can repeat that process where the only thing we change each time is the external pressure value. Figure 1 shows the crystal structure of our material in a 2-europium supercell, where these two chunks are each one primitive cell. The pink atoms are europium, green are zinc, and gray are arsenic. The red arrows are the magnetization vectors, or the spin directions, and the way they're opposite of each other, layer by layer, is an A-type antiferromagnetism. As I mentioned in the abstract, the software we used were VASP to run the calculations through CHIHA, and VESTA to view and build the materials. To submit a calculation to VASP, you need 5 files in the folder: the postcar, incar, potcar, k-points, and the job script. The postcar lists the coordinate positions and elements of each ion, and the order of the elements in this file is followed by all the others. So if you say EU, ZN, AS in that order, and then later you enter the parameters as a series of numbers, the first will be assigned to EU, the next to ZN, and the last to AS. The file that holds these parameters is called the incar, which determines what type of simulation is run, like whether it will be self-consistent or include spin-orbit coupling. All of those physical parameters in the calculation. Then, the potcar is how you give it the pseudopotential of each element, and these are available in the VASP database. For the EU, ZN, AS pseudopotential, you would paste the individual entire potcar of each element one after the other into one file. Then, the k-points file describes the k-point sampling mesh of the Brillouin zone. This is where you would outline the k-paths needed for the band structure calculation. Then, finally, the job script is how you submit all of this to the supercomputer, and its parameters are for non-physics things, like how many nodes will be used and how long the calculation has to run for. So before a calculation can be run for final results, it has to be optimized first. Figure 2 shows one of these optimization tests for the n-cut value, or energy cutoff. The higher this value is, the more computational work is required, so it's best to select the first value where the ones afterwards have less than 1,000th of an electron-volt difference in the free energy produced by the calculation run with that value. The time it takes to run a calculation, and whether it's able to converge in this time, are very important factors in the computational process. This is why we were unable to finish all of our calculations in the span of the REU. One simulation can take days just to optimize it, and if there are errors in the inputs, it must be started over entirely, which could take more days to finish. For a better understanding of what the K-point mesh is actually sampling, Figure 3 shows the Brillouin zone of a hexagon lattice. This is the path we would take to get our band structure, from gamma to M to K to gamma again to A to L. The path from gamma to A along the C direction is the region we're most interested in, as that's where the gap can potentially close under pressure. Now, Figure 4 shows the band structures presented by Wang et al. Of europium cadmium arsenide and europium zinc arsenide. This is the Dirac point where the bands touch in the cadmium material, and this is the narrow band gap in the zinc material where the bands could touch as well under pressure. These both came from calculations where they relaxed the structure, added the Hubbard U energy offset, and added spin-orbit coupling. They also set up their material's antiferromagnetism to be A-type because they found through their calculations that that was the type best suited to the real-life material. As for the results of our calculations, I'll first begin by showing you the experimental results from Dr. B's lab that started this journey. This is the absorption spectra from a range of pressures. As you can see, under higher pressure, the absorption magnitude is larger. This implies that the band gap is narrowing, as more photons would be able to excite electrons from the valence band to the conduction band if the energy barrier between them is smaller. This plot is a diffraction pattern, or XRD spectrum, also under a range of external pressures. The fact that these peaks don't change position in degrees very much, even though they decrease in magnitude, implies that this structure is keeping its stability even under the intense pressure. This last plot is the Néel temperature, or magnetic ordering temperature, over each external pressure. This temperature is the point above which the material goes from antiferromagnetic to paramagnetic. We want the material to be antiferromagnetic, and cooling it down requires more resources, so a higher Néel temperature is what we want, which, as you can see, it does increase quite a bit with the increase of external pressure. Moving on to our own results, Table 1 shows the total magnetization in Bohr magnetons from the calculations with and without the Hubbard U. The Hubbard U is an energy offset that we add to our calculations to account for real-life forces that the simulation wouldn't have already accounted for on its own, making the calculation more accurate. The paper we referenced by Wang et al. Found a magnetization of about 7 Bohr magnetons in their results, so this factor did bring our results closer to what we would expect. Also, an important thing to note is that the magnetizations are exactly opposite of each other in both cases. This is a characteristic of the antiferromagnetism. After adding the Hubbard U but without the spin-orbit coupling, our band structure and total density of states results are pictured here in Figure 6. Comparing this band structure to that of the reference in Figure 4, they are very similar with only slight differences. These differences are likely due to the lack of spin-orbit coupling, which we just haven't had enough time to add yet. But so far, comparing these two, it already looks promising how similar they are. As for the density of states plot, an important takeaway here is that it's separated into the spin-up and spin-down components. This is due to the antiferromagnetic ordering. Because of Kramer's degeneracy, the spin distinction wouldn't be present in the band structure even though it's antiferromagnetic, so the density of states is important to show the spin-up and spin-down contributions separately. Though we don't yet have the computational results for the Hubbard U and spin-orbit coupling together, the results from just adding the Hubbard U yield promising potential. The experimental data from Dr. B's lab already shows that we're onto something. It's just a matter of finishing the ambient condition calculations and moving on to test it under a range of external pressures. This research will be continued after the REU is over, hopefully culminating in the publication of a paper. I would like to thank Dr. Zhu, as well as Jia and Naomi, for being excellent mentors and teammates. It has been especially rewarding to work with Jia and Naomi as teammates, as I don't often get to experience working with other women in STEM. In my last 2 REUs, I worked with only men, and I'm often the only girl in my classes at my own college, so this was really special. Being able to talk and giggle with them in our weekly Zoom meetings has kept me afloat in some of the struggles I've faced in this program. I would also like to thank the National Science Foundation for funding this REU, and you, the viewers, for your attention.